The Illuminating World of Light with Max Axiom, Super Scientist, by Emily Sohn, illustrated by Nick Darrington. Section 1. I see the light. With a sudden flash of lightning, super scientist Max Axiom begins an adventure in light. What was that? It's okay, Spark. It's just a little thunder and lightning from a passing storm. Actually, Spark, if you could understand how light works, things like lightning wouldn't be so scary. Light is a big deal. Can you imagine life without it? Earth would have no day or night, and rainbows wouldn't arc across the sky. Light is a very important scientific concept. I think it's time to give it a closer look. Light is a type of energy. In fact, sunlight is our main source of energy on Earth. Don't believe me? Take a look at a typical food chain. Plants use sunlight to make food in a process called photosynthesis. This food allows plants to grow. Plants then provide food for animals. In turn, these plant-eating animals are a food source for meat-eating animals. As you can see, all life on Earth depends on the sun's light, including us. Let's check out how the sun makes this energy. The sun is a star made primarily of the gases hydrogen and helium. The sun is so big that atoms at the core get crammed in really close together. The intense pressure causes hydrogen atoms to combine, creating helium atoms. This process is called nuclear fusion. Fusion releases huge amounts of energy. That energy comes streaming to Earth in the form of invisible waves, also known as light. Energy waves that travel through space from the sun are similar to waves that move through water. We call the length of a wave its wavelength. We measure wavelengths by the distance between two wave peaks. Smaller wavelengths move more quickly and carry more energy than larger ones. Sunlight includes wavelengths that are very small, very large, and everything in between. Like water waves, light waves with short wavelengths have more energy than waves with long wavelengths. The whole range of energy that comes from the sun is called the electromagnetic spectrum. The visible light we see makes up only a very small part of the spectrum. Each type of wave has its own properties. And many waves play important roles in our lives, even if we can't see them. Radio waves, X-rays, microwaves, ultraviolet light, infrared light. Everything that releases heat gives off infrared light. The military uses infrared cameras to see people and other objects during night missions. The cameras help soldiers see in total darkness because the cameras can detect the infrared light. Section 2. What light can do. You probably think of sunlight as white and bright. But hidden inside visible light are all the colors of the rainbow. This clear piece of glass is a prism. Like the water droplets from the sprinkler, it makes rainbows too. When white light passes through a prism, it bends and splits apart. The prism shows us the colors of the rainbow that make up white light. On the electromagnetic spectrum, red, orange, yellow, green, blue, indigo, and violet line up by the length of their waves. Red has the longest wavelength you can see. Violet has the shortest wavelength. Light has some other cool properties too. Want to know more? Let's go for a ride. If you could ride a beam of light, you'd be the fastest person on Earth. Light moves about 186,000 miles or 299,300 kilometers a second. Nothing moves faster. Yee-haw! Light years. The distance light travels in a year is called a light year. 1 light year equals 6.2 trillion miles, 10 trillion kilometers. The closest star to Earth after the Sun is 4.3 light years away. Although light moves super fast, we can see how it behaves when it hits objects around us. For instance, have you ever wondered why you can see yourself in a mirror? It's because light bounces off shiny surfaces and back to your eyes. This bouncing is called reflection. Reflection. Light reflects off more than just mirrors. Everything you see reflects some light. For example, you can see the moon because sunlight reflects off its surface and into your eyes. Light interacts with different objects in different ways. Clear glass is transparent. Light passes through transparent objects, allowing us to see through them to the other side. But objects like this painting are opaque. Light can't pass through opaque objects. Therefore, we can't see through them to the other side. Because opaque objects block light, we see shadows or dark spots behind them. Of course, not all objects are completely transparent or totally opaque. Some objects are translucent. For example, this stained glass window lets some light through, but we can't see through it to the other side.
Look, Mom! That's Max Axiom. He visited my science class last week.
It's good to see you again, Carla. May I borrow one of your drinks for a moment?
Sure. Why?
Because it's the perfect example of refracting light. Have you ever noticed that objects look distorted when you dunk them in a glass of water?
You're right!
It looks like the straw is broken.
But you know that it's not. It's an optical illusion. Our ability to see the straw depends on light reflecting off of it and into our eyes. But when light passes through transparent materials like water and glass, it changes speed and bends. The light coming from the bottom half of the straw passes through both the water and the glass. The two transparent materials bend or refract light so much the straw looks broken. When I pull the straw out, we see that it was in one piece all along.
Cool!
never knew light could bend.
Section 3. What we can do with light. One of the most important things we do with light is see. Let's take a look at how our eyes use light. The human eye is only about 1 inch tall and 1 inch wide, but it's a complicated organ. Light comes in through the cornea and travels to the pupil. The pupil changes size to let in more or less light, depending on how bright it is outside. The light then passes through a lens. The lens bends the light and focuses it upside down on the retina at the back of the eye. The retina has 2 types of cells called rods and cones. Rods sense black and white. Cones sense color and details. The optic nerve carries information about what you see to your brain. Your brain turns the images it receives back over so you see the world right side up. Our eyes have built-in lenses to focus light, but some tools use convex and concave lenses to help people see better. A convex lens is thicker in the middle than around the edges. Light rays passing through it bend inward. A concave lens is thinner in the middle than around the edges. This lens bends light outward. Glasses use either convex or concave lenses to correct vision. Nearsighted people see close objects clearly, but objects in the distance look blurry. They wear glasses with concave lenses to see clearly. Farsighted people see distant objects clearly, but objects that are close look blurry. They wear glasses with convex lenses to correct their vision. Concave lens for nearsighted eye. Convex lens for farsighted eye. Magnifying glasses and microscopes use lenses too. A magnifying glass uses a convex lens to make small objects look bigger. A microscope uses 2 convex lenses to make things as tiny as plant cells appear bigger. Of course, no study of light is complete without mentioning light amplification by stimulated emission of radiation, or laser for short. A little fog in the air will show the difference between laser light and light from a flashlight. Check out how light from a flashlight spreads out, while the laser light forms a skinny beam. The flashlight produces white light, which, like sunlight, is made up of all the colors of the rainbow. But the laser produces only one wavelength of light that moves in just one direction. Laser light can be focused onto a very small spot, making it easy to aim. Some lasers are so powerful that they can cut through steel. But less powerful lasers are used to play CDs and DVDs, do eye surgery, and scan barcodes. More about lasers. Lasers use mirrors to bounce light back and forth until it is all moving in one focused direction. The types of atoms inside a laser determine what wavelength will come out. Ruby field lasers give off red light. Carbon dioxide field lasers give off infrared light, which can be hot enough to cut metal. Section 4. Energy conversion. I have so much energy when the sun is high, but as the sun droops, my energy fades as well.
Hey, Max!
Hey, kids, what are you doing?
We're using the sun to bake cookies.
Very clever. You're using solar energy and converting it into heat.
We are?
Sunlight does a lot more than just let us see. Sunlight or solar energy can become heat, enough heat to bake cookies in a solar oven. Thanks for the cookies.
See you later, Max!
Solar energy can also be changed into electricity. In fact, some homes collect power with solar cells. Hi, Spark. It's been a long day. The sun isn't the only source of light, of course. These days, we spend most of our time around light bulbs, digital clocks, video games, and other glowing objects. All of these items use electricity, and electricity comes from burning coal, splitting atoms in nuclear power plants, or harnessing wind, water, and sunlight. Our household gadgets convert electricity back into light, heat, and sound. I sure used a lot of energy exploring light today. Now I'm ready for a little darkness.